Hi, and welcome back to the FE exam review series. If you're new here, my name is Ryan, and today I want to solve this FE exam heat transfer problem for you step by step and make sure that we're referencing the official FE reference manual. If we check in the FE mechanical specification, this problem is related to subsection A and B in the heat transfer section, conduction and convection, but it's mostly a conduction problem. Okay, we're going to jump right into the solution and really refresh those fundamentals. It says that a square fin with a thermal conductivity of 150 watts per meter Kelvin. So K is equal to 150 watts per meter Kelvin. We're given a side length of 5 centimeters, and we know that this is a square fin. Side length is 5 centimeters, and it's a square fin. 5 centimeters is 0.05 meters. We have two metal plates on both ends. They're both maintained at a temperature of 90 degrees Celsius. Additionally, there's a space between the plates of 0.4 meters, and the fin is exposed to air at 25 degrees Celsius and a convection coefficient equal to 40 watts per meter squared Kelvin, and we're asked for what the heat transfer from the fin is. Okay, and if we recall, the heat transfer options were measured in watts, so we're technically asking for the heat transfer rate. Sometimes the word heat transfer and heat transfer rate are used interchangeably, so just make sure you keep note of that. What's very important when we're looking at fin problems is evaluating exactly what the boundary conditions are. We need to know, is it going to be an adiabatic fin tip? Is it going to be convection at the fin tip? What exactly is it going to be so that we know what the appropriate equation to use is? If we kind of sketch out what the temperature distribution would be for our symmetric scenario here, we have a temperature as a function of position. You can kind of picture that the ends will be at 90 degrees Celsius, the elevated temperature, and that there would be heat loss, kind of a lower temperature as you travel along the length of the fin, where it would return back to that higher temperature at the two metal plates. And you know that this scenario is symmetric and the temperature distribution inside the fin is continuous and smooth. If we look at the center of the fin, what we have is that the center of the fin, it has a zero value derivative or a zero slope. dTdx is equal to 0. Fundamentally, if we think about what Fourier's law of conduction is, Fourier's law of conduction says that the rate of heat transfer is equal to negative Ka dTdx. But if in the center we have dTdx is equal to 0, that means the heat transfer at the center location of that pin, at the center location of that square fin is going to be equal to 0. So it's as if we had an adiabatic tip in the center. If we cut it in half and we did that, we double the heat transfer rate here. Two adiabatic fin tips, two adiabatic. It's as if we had two fins, both with adiabatic tips. So what our plan is going to be is to find that adiabatic fin tip equation, and we're going to double the heat transfer rate. So I'm going to put a 2 here automatically, and we're going to compile the formula from the FE reference manual. If we check inside the FE reference manual on page 209 of the version 10.4 of the FE reference manual, the most up-to-date one, you can see some things right here related to fins. We have the heat transfer rate for an adiabatic fin tip. You can see here it says, assuming negligible heat transfer from the tip. We have all the parameters defined here, as well as the corrected fin length. Now, the corrected fin length is what we use if we have convection at the tip. Because the solution here for convection at the tip as well as an adiabatic tip are very similar, what we do is we correct the fin length. If we have convection at the tip, we extend it. And so instead of convecting out the tip, we convect out the surface. And we're going to talk about that a little bit more. But let's go ahead and grab this equation and put it right here where we're solving the problem. Okay, let's clear up that corrected fin length, and I'm going to justify to you why I'm saying we don't really have to use this. Let's say that I had a fin, and at the tip of this fin, I have convection. Because their solutions are similar, instead of using the convection at the tip scenario, what we do is we extend the fin length by an amount, I'm going to call it delta L sub C. And delta L sub C is what we get if we take the cross-sectional area that's exposed to convection and we extend it to be on the surface instead of at that tip. So we would take the perimeter and multiply it by delta L sub C. So now the same amount of cross-sectional area that we originally had at the tip, we moved it to the outer surface. So that delta L sub C is equal to the cross-sectional area over the perimeter. We would add that on to the original fin length to get a corrected fin length. L plus the delta L sub C is A sub C over P. So you see that we really only use that if we had convection at the tip. For our case, we have two fins, both with adiabatic tips, so L sub C is not applicable for us. We're going to cross that out, and we're just going to use half of the actual length here, but double our heat transfer rate. Okay, now that we cleared that up, we're going to go ahead and write down some of these things. I'm going to note that the perimeter here, since we have a square, is 4S, and the cross-sectional area is equal to 4. The cross-sectional area is just equal to S squared. Now I'm seeing a product of the perimeter and cross-sectional area, and in this M term, which is this, it's equal to the square root of H over K, P over A sub C. I'm seeing a ratio of the perimeter to the cross-sectional area, so I'm going to take the product and the ratio and just reduce those. P over A sub C is equal to 4S over S squared. That's 4 over S. So we have that one. Now what about the product? P times AC. That's equal to 4S multiplied by S squared. That's 4S cubed. Now that we have all of that, let's go ahead and plug into our formula. Remember that we double the heat transfer rate and we cut the actual fin length in half. So our L here is equal to 0.2 meters, half the spacing. And we already accounted for the fact that there's two of them by doubling that Q. We have the square root of P times A sub C is 4S cubed that we computed below, and that's H times K. Additionally, we have the difference between the base and the kind of free stream fluid. The base was at 90 and the free stream is at 25. That will put us at 65 degrees of delta. So I'm just going to write that down. And then we have the hyperbolic tangent of M, which was that ratio that we had involving the ratio of the perimeter to the cross-sectional area. So I know I'm going to have a 4 over S term here. And then I also have a ratio of H over K. And that's multiplied by the length of the fin. Okay, so this is our entire formula. What we're going to do is plug into this formula and get a final answer. Before we solve the rest of the problem, if you're enjoying this video and you're learning something, consider leaving a like and subscribing for more content like this. Additionally, if you're prepping for the FE Mechanical exam and looking for a resource that will help you pass, consider checking out my software, FE Interactive. It's the third link in the description below, and it'll give you access to multiple different sections, practice exams, review and improve sections, as well as a tips and tricks section, which helps you use your calculator better and save time on test day. An analytics page, which ties all of the different pages together. You get data for each of those pages, where you can view, for instance, how you did on each exam, as well as a detailed solution manual for each exam, so you know exactly where you're making the mistakes, what exactly is the misunderstanding coming from, and all of those are tied together with an overall data point. The overall data point can be reorganized in terms of performance so that you know, what are my top 3 subjects? What are my bottom 3 subjects? Having this kind of data is super valuable since it helps you isolate your weaker points and fortify your strong ones. I'm confident that my software, FE Interactive, will help you pass the FE Mechanical exam. And again, you can check it out using the third link in the description below. You get 2 months of access for $29.99. Let's get back into the video. Okay, you can see here that we got a final answer of 163.8 after plugging in. Before I was missing a square root here, so make sure that you include that in the calculation. Okay, let's go ahead and check the answer and make sure that we're correct. If we got an impart our answer of approximately 163.8, we see we got it correct. And you can view the written explanation. So if you don't have time, you can always try these problems using the first link in the description below. That'll take you to this set of problems. It's around 40 problems thus far, and you can read through the type solution here. If you learned something from this video and you like content like this, consider leaving a like and subscribing for more videos like this. Thanks for watching. I'll see you in the next video. Goodbye.